Okay. So remember, we're using ANOVA when we have 3 or more groups. That basically, and what is really important to keep in mind, that the dependent variable will be seen on the y-axis, and that's a scale variable. We have an independent nominal categorical variable, which basically has 3 or more levels, which basically defines the groupings. So that means that all of these 4 conditions here are basically 4 different groups, notably in distinction to the within groups ANOVA, 4 distinctly different groups where participants are not repeatedly occurring in different situations or in different conditions or different levels of the independent variable. So you're doing the exercise because you want to avoid the increase of a type 1 error, where the type 1 error essentially comes at one comparison where you have 2 means. That would literally be a t-distribution. If you have 3 or more, you're basically inflating the type 1 error up to 14.3%. If you are up at 7 means with 21 comparisons resulting from those comparisons, you end up with a 66% type 1 error. That means that at least one of these comparisons will be significantly different from the other due to pure chance, due to pure sampling and a sampling error, pretty much. So therefore, the F distribution was introduced to avoid this from happening. Again, this is a super important table to basically distinguish between the 3 different comparison distributions. So you have with a STAT test, you have always 1 sample only. So when you have 1 sample, you distinguish between a STAT test or a t-test. That is essentially what you need to distinguish. And the distinguishing factor is whether you know the variability. If you have the variability of the population given, you have a sigma given, then you will choose a STAT test. If you have it, if you have the sigma not given and you need to estimate it from your sample, then you're basically resorting to a t-distribution. Keep in mind, where t-distribution was invented was in a brewery where they basically wanted to meet a certain quality criterion, and they couldn't sample the entire population of beer of the day that they produced. So they needed to take small sample and estimate the variability to make sure that each of these samples and the current hour of production was corresponding with that quality criterion, that reference value they wanted to achieve with their samples. So this is where it came from, and this is how it found its way into public health and data analytics. So with 2 samples, you're comparing the differences. So with a paired sample t-test, you compare the differences of from before to after. So basically your comparison distribution is a t-distribution, but it's basically 2 samples before and after, but you're collapsing it to 1 sample by basically calculating the difference. So the comparison distribution is the t-distribution, but only 1 sample. It's the comparison of the mean of the difference scores. So when you have 2 samples, you are comparing 2 independent samples from which you draw small little random subsamples, and you create a difference, like a little mean difference or difference between those means of these little subsamples. You drop these samples back and you just keep this random mean, and you do that repeatedly and you get a distribution of the differences between means. So that's important to keep in mind. So it's a different process. Therefore, you need to account for the variability from both of these samples, where you draw these hypothetical subsamples out that you use for the estimation of the standard error of the mean differences. And yeah, that's why you need to pool the variance and then basically utilize the pooled variance to get a standard error of the mean differences. When you have 3 or more samples, you basically you do have indeed for each of your subsamples a sample, and you are basically, what you do is you're comparing the variability within the sample to the variability between the means of these samples. And that essentially gives you an idea of that relationship. And this relationship can be tested against an F distribution. And this is what we're recapping today. Just know the term. So it's basically you analyze the variability to compare the means by variance between groups and variance within groups. This ratio is basically your F. And this ratio, you're basically comparing to your, no, is it not? Here, against your F distribution. The F distribution as compared to the T distribution, which has the shape more or less of a normal distribution. And you're changing your approach from a set distribution, which is a perfect normal distribution, presumed perfect normal distribution. The T distribution has the shape of a normal distribution, but you need to kind of play with the division of the variability when you estimate it. That's why you divide your variance by the degrees of freedom and not by the sample size as you would do for the population. Therefore, you kind of widen the estimate of your normal distribution shape, and you kind of approximate the normal distribution. With an F distribution, that is a unimodal right-skewed distribution with a critical value that is a one-sided critical value. That means your F, per definition, if you have a ratio, you're calculating a ratio, that ratio, there are two factors that get this ratio up. That's the variance between groups. If that increases, your F gets larger. If your variance within groups gets smaller, then your F gets larger. What does that mean? You're testing, yes. The ratio of variance between groups and variance within groups. Remember the example of, and that's my favorite graph, remember the example of the 4 societies. We have small little samples of members of that society that played the dictator game. They basically show a within groups variance. There's a variability within that group, right? And that's true for all the 3 groups. And then you have variability that is basically built by the variability from the individual group mean to your grand mean, to that black line. And you're relating these 2 variabilities against each other. And by building this ratio, you get an estimate of how likely is it that at least one of these groups is different from the other. Exactly. So you first go and you calculate your between groups variability over the within groups variability, and that's that ratio you're using then to compare against your F distribution. So this ratio, if the variance between the groups is getting larger, that means that the groups are further away and that variance is logically then getting larger. Or alternatively, the variance within the groups will get smaller. That gets your F up and gets it more likely past the critical value. These 2 conditions will basically drive the F higher and past the critical value. And when you think about it, you want to sense a difference. You want to know whether there's a difference between those groups. So if you have more variability between your groups as a deviation from that grand mean, that means they're further apart and likely they're more likely to be different, right? And if the variability is smaller, for example, because you have larger samples, that will drive your variability smaller arithmetically because you divide by a greater degrees of freedom. That will also get your F greater and more likely to be passing that critical value. So
the F distribution is basically based on ratio.
On this ratio.
So it's this equation, but it's kind of ratio because when you're looking at that type of graph.
Yes, so it associates with a certain degree of freedom and a certain variance, right, and a certain other variance. It distributes in that shape or form. Yes. So it's an assumption of how the population looks like. If that were from a population, this is how it would look like as a ratio. That's the underlying assumption.
So without setting, this is how we look for a given.
it's a mathematical construct. It's not something that was empirically developed. It's a mathematical construct, how you can associate the relationship of the probability of sensing a difference between those groups to your actual variability within and between groups. So that's it's basically, it is in essence a relationship between these two factors and the probability of the outcome being met. So it's a distribution of probabilities rather than actual samples. I guess that's a fair statement. Just like the normal distribution, right? If you have a population, it's fine to say, okay, so you have like between one standard deviation and the second standard deviation above the mean, you have 68% of your population. However, if you transform this now into a standard error of the mean and a hypothetical distribution of randomly sampled sample means, and you confer that principle of standardization to that normal distribution, you also you don't get a real, you get a hypothetical distribution of means of hypothetical samples that you have drawn. So this is really reflecting at that point the probability rather than actual sample. It is legitimate. It is legitimate. It's just you haven't drawn 200 samples if you're mapping out the standard error of the mean. You just assume that given that sample size, you likely have that kind of distribution if you know the standard deviation of the population.
Okay, but either way, it would work. You're just saying
it's working, yes, but it's a mathematical rule and a mathematical estimation of that probability.
Yeah. Regardless if it's good or not.
Regardless of?
Regardless if it's grouping or not, they're still relative to comparison.
Yes, exactly. It's independent of the group. It's a general rule and a general mathematical rule how you get to the estimate of this probability. Yes. Yes. And the same with the F distribution. So it's a mathematical function that allows you to estimate the probability. And the probability distributes under this area under the curve, under this curve, which is a mathematical function essentially that has an area under the curve, which could be integrated. Then you get this area under the curve, and then you have like this critical cutoff under which you have 5% of all that area under the curve. That's beyond that point. So it becomes a reflection of the probability of one of these being different. Yeah. And that's also why the F-score table is such a complex table, because now you're not just dealing with the distribution of hypothetical sample means, it's much more complicated because you need to factor in, when it comes to variance, you need to factor in the degrees of freedom from both sides. So you need to factor in the degrees of freedom. So all these are basically a reflection of different mathematical functions because they follow a different shape if they have different degrees of freedom for the calculation of that variance that you use to calculate your ratio. It's just the F-score table is one way to do that. R, for example, and we will see that today, R is basically not using F-score table. R is using the mathematical function and is mapping that out and simulating that through and taking that actual estimate of the integrated area under the curve for estimating the exact p-value. Because this doesn't give you an exact p-value. This just gives you a threshold. And that's just, it's basically in the real world, you would quantify the exact p-value for an ANOVA.
But it's not possible.
No, p-value is a probability.
The p-value probability, I'm saying, and Z is also not.
STAT score is essentially not a probability, but it translates in one. Remember the STAT score. The STAT score, we have the STAT score table, and we find the respective STAT score, and that corresponds with a percentage. And if we looked for the percentage in a population, then we had a percentage of the population. It was like 68% of my population is between 1 and 2 standard deviations. If we're using it to test an hypothesis, this percentage is not a population anymore. At that point, it becomes a probability. It's just it's shaped it's shaped equally. The function is the same. Here, it's a different function. And that function is looking like a unimodal right-shaped distribution. So that's how it becomes the comparison distribution. Yeah. Any other questions? Okay. So this relationship that you're trying to determine is basically giving you then the possibility to test your hypothesis. Where let's keep in mind the null hypothesis of your ANOVA is basically that people living in these 4 societies, they're all the same. The mean of each of these samples is identical. Whereas the research hypothesis that at least 2 of these societies are significantly different from each other. That is the research hypothesis. So if you're rejecting the null, that's what you have to conclude and interpret. Make sure that you know how to quantify the degrees of freedom. That is like almost like a very high probability to be a question. Is like know how to calculate the degree of freedom for an ANOVA, but you know that, right? It's like it's degrees of freedom between. You take the number of groups because this is what you're calculating your variance on. So you're calculating the deviation, the squared deviations, and you divide it by the degrees of freedom, just like with the T distribution, when you estimate the standard deviation based on a sample. So you have the number of groups minus 1. That's how simple it is. Then you have degrees of freedom within, which is basically each group, each sample, and each sample size associated with the sample minus 1. And that basically gets you then the sum of degrees of freedom within. So these are all the within estimates. That's the F-score table. So here we have an ANOVA source table. Know how to read the ANOVA source table, know how to fill out the ANOVA source table. So you have the sum of squares in the first column, gives you a sum of squares between and the sum of squares within, and the sum of squares total. Then you have the degrees of freedom between, degrees of freedom within, and then you have a degrees of freedom total. Dividing the sum of squares, and this is where that relationship basically points. So this is if you have everything given in terms of sum of squares and degrees of freedom, obviously you can calculate the variance by just dividing your sum of squares by the degrees of freedom. That gets you the variance between and the variance within. Dividing that ratio is then giving you the F. So we will go through the calculation. Oh, well, let's do that actually quick since we have time. Please also open the R code. Let's do that. Let's do that actually simultaneously in Excel and R. So if you look at the code now for practice lab 4, you have, again, in the first line, you have remove all objects from the environment. So you're kicking all of these out. Then you are starting in line 7. And that's probably not working for most of you, all of you, I guess. So please select first line 5, but do not select the hashtag. And that is important because install.packages gives you basically yes.
Sorry, can you repeat what we have to do out of that? I'm just opening.
Oh, okay. Yeah. Excuse me. Yours looks different. You don't have line 5?
Line says install packages. It doesn't have a hashtag. Yeah.
Then make please sure that you have the hashtag in front of it. Place the hashtag, and then start line 5 and line 6 individually without the hashtag. And the reason for that is because if you're running the whole thing, it will install that package newly. If it does that, that takes a long time. So please only run line 5 and line 6, hashtag line 5 and line 6.
Clear the environment.
Clear the environment, put a hashtag in front of line 5 and line 6, and then only run everything after the hashtag without the hashtag once, because that installs the package, and line 7 and line 8 runs the package. It's required but not installed.
Required but not installed.
It just shows on the top like a yellow triangle with like a kind of like a warning.
Yes, can you click install on the triangle? Show me.
Hey, it's installed.
Okay, now it's installing.
Mine was like this now.
Yeah, that's good. That's good. That's installing. Okay. So please put a hashtag in front of install.packages, like exactly how it is here. And then run only everything following that hashtag. Yeah, 5 and 6. So you run install.packages and you're running that down, but without the hashtag. This command will install those packages. So if you do that both for line 5 and line 6, next step, you just need to go on line 7 and line 8.
There's no package called.
Yeah, you need to run line 5 and line 6 first,
Yeah, I did that.
but without the hashtag.
Oh, you add the hashtag after.
Correct.
You do it to get like when you highlight 5 and do control and enter and then highlight 6, that line 6 rather than
No, you don't need to highlight. Well, do the same for 6. Yes, so you do 5 and 6.
But when I do it, like something else, like red words show up.
Yes, that's the installation. That's the actual installation, which looks like this, right? Yes. Yeah, that's good. Yeah, that's going crazy. Exactly. It's going to explode in a second. No, nothing's going to happen. No, this is installation. It's automatically now. It's going to the internet. It gets down little chunks and installs those.
Okay, so should I delete this? Like,
No. Just let it do its job. That's fine. It's doing the same here. I reran it. Then at one point it's finished. Do the same thing now for line 6 minus the hashtag.
then I add the hashtag afterwards.
Yes, the hashtag. So the final product, if it asks you this for line 6, say yes.
I get that. Don't have
That's okay. That's okay. No problem.
I'm very sure.
It's just telling me that I can find the downloaded binary packages, and then it tells me something. Like
Good. Good. That's fun.
Like mine, you have like a lot more stuff loading.
Yeah, that doesn't matter. It knows what it does. Don't worry about it. Nothing you need to do.
You know, at the end before we submit, we clear the whole thing and then we run the whole thing.
Exactly.
How are we gonna do that if we don't want?
You don't have to do it. That's why we're doing it now. That's why it's so painful now. Because hashtagging out, as you remember, the hashtag basically comments out that entire line. You don't have to run it again. This is basically just a comment at this point. So only if you leave the hashtag out and only you're selecting everything after the hashtag, then it basically activates it as a command. That's why we're doing it. So we're basically helping our future self who wants to run the entire code, doesn't have to run the whole installation again. That's the idea. You're welcome. Well, It's lazy loading, as you can. It's a little slower, but it's fine. Okay, good. So this is installation of packages. So what that is basically it's a pre-programmed code that R has provided, basically installs packages that provide R with functions. And these functions you can then use to do various things. And one of these things is to run an ANOVA. And so there are base kind of functions from base R, which is R in its purest form, or there are functions that are coming from packages, and usually those are a little bit more sophisticated and more advanced methods. And that's again to the advantages of R, and R is very, very specifically designed for statistical computing, whereas other softwares, like for example Python, they are more advanced, they're more computer programming languages almost. But Python can also be used for analytic purposes. But both of these, one thing they have in common, they have a very updated and state-of-the-art package library, which you can use to basically find everything that has been published on planet Earth, where basically everybody puts up his or her own code or packages. So let's assume you are interested in an advanced machine learning algorithm. And this is nowadays everybody speaks AI and machine learning. So these algorithms are getting more and more popular, and you have various algorithms for various purposes. Probably all you have used, what is it called, that GPT, the funny tool and an online AI tool. You can also get to find what has been published online by getting an account with GitHub. And every coder, every developer, every statistician, particularly those involved in more advanced methods, will have a GitHub account and will basically share his or her codes online to the community. You remember the open science kind of endeavor, open science mindset of the scientific community. This goes in the same directions. They're all sharing their things. It's a very sharing and it's a very collaborative community. That's true for coders. That's true for researchers in general. You have, for example, and this I'm just giving you this quickly. You also have what is called a forum. If you have an R problem, or a Python problem for that matter, those of you that go into computer science or somewhere in that direction, you want to know Stack Overflow. Stack Overflow is basically, it's a community of developers, coders, statisticians, etc. Everybody who uses some programming language will basically have an account on these fora. So Stack Overflow is just one of them. But basically, they are on these fora discussing technical problems and specific problems they have encountered running their analysis. And you will, to this day, I have maybe a handful of problems I came across, and I come across a lot of problems that I have not found a solution in Stack Overflow or a related forum. So there is such an ongoing discussion on so many topics. You have administrators then connecting the comments and the discussion threads. So there's a solution for all your problems. So that's just a little bit from my world. Okay. So, but we have now installed dplyr and R statics, two quite standard packages. If we go now in lines 7 and 8, we're running now the codes that will start these two packages. And then we're basically getting these installed. And then we can run 12 and 13. 12 and 13 is basically creating a data frame containing the data that we have analyzed in Excel the other day. So it is already in a long format. You remember long format? That's when you get this wide format where you have the groupings. Nope. Still a spreadsheet. Okay. So we have here a wide format where the groupings is basically arranged. So here's actually a row, it's not a column. So that's the grouping. That's the levels of your independent variable. Whereas this is your dependent variable, all of these values. So the long format here is basically just a rearranged format that we have created here on the right, where we basically have brought our data in the long format. That's pretty much the same as this. Same thing. Remember now what we needed to calculate. We have as items that were to be calculated, we needed, sorry for that. We needed 3 different variances, or sum of squares. Remember, sum of squares divided by degrees of freedom gets you to the variance. So you basically, you have the societies arranged in long format, you have the scores arranged in long format. You use all these scores to calculate your grand mean. You calculate then on a group level your group mean. You arrange your group mean in a shape that all of these are basically aligning with the respective item, and you utilize this to calculate your deviations between. So the deviations between is basically nothing else but the individual scores minus the group mean. And you do that for each of your entries. Then you're basically squaring it and you're summing it up. When you have the deviations within, you're basically taking, oh no, that was actually grand mean, sorry for that. It's basically the group mean minus the grand mean. And this is the deviation within, that's the individual score minus the group mean. That gets you the variation within. Keep in mind, this is exactly this graph, which I've shown quite frequently today. But it is my favorite graph because it really depicts this quite nicely. Good. So we have now calculated the within and the between sum of squares. And now we need a total sum of squares, and that is nothing else but the individual scores minus the grand mean squared. Gets you the total. These 3 arithmetically need to add up. So the sum of squares within and the sum of and sum of squares within need to add up to the sum of square total. And here we actually see that. So it's not only that, it's also the sum of these 2. No. So these 2 are basically adding up. Then you have the degrees of freedom between and within, and adds up to a total. Dividing these sum of squares by the degrees of freedom will then allow you to get to the variance. And calculating that ratio between and within will then allow you to calculate and estimate your F. So that F, you compare then against your F-score table, and then you calculate an effect size, which is 0.74, which is quite a large effect size. Good. So that's this. So how do you do that in R? You're doing that in R by basically taking your data frame And remember how you do that data frame. You get a data frame where you have societies basically included here in as a factor. And you have then the corresponding scores. So as a consequence of that, you can also do summary of your DF1. And that command basically gets you an overview of the entries for your different societies. And it gets you an, yeah, sure. Summary DF. So if you have a DF, you see as soon as you ran line 12 and line 13, you get objects on the right. So this object is basically the object that you're analyzing in the following. So that's your object with those two variables. That's your R spreadsheet.
So which one did you just run? It's
12 and 13. Yes. So for the summary of DF1. So you can then run line 16.
I don't have that 14.
Yep, you need to write it.
We don't run mine, right?
You can. It's commented out, so it's just a comment.
Then run.
Yeah. So now you can next you run line 16 to 18. That gets you DF2. We can, yeah, we can. So that's basically now the within group ANOVA. So remember how we did the within groups ANOVA, which basically is our beer tasting. And the beer tasting basically then is being brought in a long format, just like before, with the additional column of participant number, because each participant has drank the same beer. So in 3 different levels of the independent variable, that's 3 different beers. So we have then a little bit more to calculate. So we have here the mean, the group mean. So that's the group mean for those 3 different beers. Then we have the subject mean. So that was the mean for each individual for all 3 conditions, because we wanted to quantify the subject variability, the variance subject, a sum of square subject. Calculating now the deviation of each individual entry from the grand mean will then allow you to get the sum of squares total. Calculating now the mean minus the grand mean gets you the deviation of each individual mean. What's the problem?
Just had a question about what subject M was. What was that referring to?
That's the subject mean.
Subject to.
So if you click on the formula, it shows you what it is. So it's an average of each individual participant's beer rating. Thereby you get a mean for each subject. So you get 5 different means for each subject.
One, and all.
For each subject, correct. You get an average of subject 1 drinks a cheap beer, subject 1 drinks a mid-range beer, subject 1 drinks a high-end beer. You get one mean of these 3 for each subject, and you add this 3 times for each time you drink a beer to preserve the degrees of freedom. Then you get 5 different means, and this subject mean also has a grand mean. And that grand mean is what you're subtracting it from. So you basically calculate here the M participant minus the grand mean. So the grand mean is your solid reference.
Grand for that.
No, it's the grand. Well, you get a mean. It's like a group mean. It's not a group mean. It's a participant mean. And then you reference this participant mean to your grant mean to see how much variability do we see. And that's how you quantify it. And by quantifying it, you get a means to decrease your sum of squares within. So basically, if you say, okay, I have 3 sources of variability. Variability 1 is within my group, within that beer, I have some variability because different people like beers in a different way, right? There's like somebody may like the cheap beer more than the high-end beer, not based on this data. But secondly, you have a variability according to the individual's preferences. So John may like different beers than Jack. So it's individual preference. So you get this subject-specific variability in taste preferences kind of incorporated in your estimate of the variability. And then lastly, you get the pure difference between the groups. So if I serve a high-end beer, more likely that the participants will like that beer more than the cheap beer. So what you do now, you get a total variability. So this is all your variability for all your ratings. You're subtracting from that the subject-specific sum of squares, that variability from the subject you take out because you don't want to deal with the individual taste preferences. You just want to know whether these beers are actually different. So by taking the subject out and subtracting this from the total, you actually get a modified, smaller sum of squares within. So a true variability within the group. And that is the variability that you then use to calculate the F ratio, to get that pure effect of the variability between the groups. So you take the subject-specific individual preferences out of that equation, and you say, hey, that individual differed quite a bit or didn't differ that much. If there are a lot of differences in the individual ratings of the subject, this will increase your variability of the within groups variability. And as we know from the equation, it's between groups variance over within groups variance. So if the within groups variance is high, you're less likely to get a large F score. So it's less likely to not show a significant difference. But if you diminish your within groups variance by taking out the subject variance, you're more likely to get a larger F because you see the true effect between the groups. Does that make it clearer? Yeah? Okay. And lastly, once you have done that, you just punch this into an over source table. You have between groups, within groups, subject sum of squares, and the sum of this adds up to 2117. You get the degrees of freedom. This is 3 groups. Degrees of freedom is 2. Within groups, it's within groups is 4 multiplied by 2. Because it's degrees of freedom for each group. No, it's what I'm saying. No, it's 2 by 4. So it's 4 individual in each group. Its degrees of freedom is 2. So 2 by 4 is 8. Its degrees of freedom subject is 5 minus 1, and total is the sum of these 3. And then you just calculate the variances, and you get to your 2 F scores, where only the first one is being interpreted. That's important. Good. So that was within groups and over in a very quick recap. So now to R. So we have degrees of freedom. We know data frame 1. We have data frame 1. Calculated and built. Now we look at data frame 2.
Should we do that again?
Yeah. So data frame 2 basically shows a numerical variable for participant ID. We have 1, 2, 3, 4, 5. you have 5 entries for each beer type. You have cheap, high, and mid-range, each with 5 entries. And each of these 5 cars went through these 3 ratings. Then we have the rating ranging from 23 to 65. Good. So now we need to do a couple of things. And this is now why we installed dplyr. So dplyr is a wonderful package, and it does something that is basically giving you group-wise summarizations. If you group by DF1 and society, and you're summarizing, and you give it count, mean, and standard deviation, you get exactly these values. So that's one way how you can look at this data. And if you run 21 to 25, you're getting exactly that data. Yes.
How did you get the max was 62 or 64? Did you change like any numbers?
No, I just changed. I ran summary DF2. This one. It's just a summary. Yes.
Mine says there was an error.
You added that in again?
Yeah.
Says that there's an error in group underscore by DF1 society.
Did you select everything?
Yeah, I did in 21.
Did you run line 12 and 13? So if you run these 3, and then you go back down to group by, you got that?
Should I just do it again?
Probably. So, Control and L. So the same exercise. So again, summarize. So what you do here with group by, you're basically passing on the commands to R to take DF2, which is our beer example, stratify it as per beer type, pack it in this thing, and that's called that's called the dplyr language a pipe. You're basically piping it, so that means you're moving it forward to a function, and the function here is summarize. And summarize basically has as a possible subfunction, it can give you a count, which is just counting the number of entries. It can give you a mean, which the mean is here added with na.rm equals true. That means na, those are missing values. If there are missing values in there, remove them, true. So everything, every missing value and every entry for which the criterion for missing value is true, remove it. That's important because if you have a missing value, that is basically resulting in a division by 0, you basically have a problem arithmetically. Yes. Control L. No. So if we're doing the grouping now according to the beer type, we're basically getting here now what we have seen also in our group means. So we're seeing cheap beer is low, and we have mid-range beer is still low, high-end beer considerably high, also notably with higher variability. The standard deviation is large. Then what we can also do, and that's nice for in addition. So again, same command. We're grouping our DF2 now by the participant. We again do the summary, count, mean, standard deviation. We get now participant means and participant standard deviations. So these are our participants' standard deviations. So it's 41, 50.7, 44, 37.8, and 29.7, which is here the same as we have for these calculations. So that's basically this. And now it's getting interesting because now we're getting to our actual ANOVA. So we have two different ANOVAs. We have an ANOVA one-way between group and ANOVA within group. All right. If we do an ANOVA between group, we take our DF1, which are our societies, right? So ANOVA 1 equals, so that's the R equal sign. AOV, that's a base R command for an ANOVA. The score, so we know that if we do LSDF1, we see what's contained. So if we do LSDF1, so we do score, and here this tilde, that means as a function of, so it's basically, this is defining dependent variable and independent variable. On the left of the tilde, you have the dependent variable. On the right of the tilde, you have the independent variable. So basically, you're running that as a function of society. What happens now is you get now ANOVA 1 as an object in your environment. And this ANOVA 1 is basically your ANOVA. So it packed it inside this object. You have coefficients, you have residuals, you have effects, you have rank, you have fitted values, contrasts. Well, let's not go into too much detail what all of this is. But basically with summary ANOVA 1, you're basically getting the R ANOVA source table. And that ANOVA source table is basically consistent with the source table as we have done it for our society example. It looks a little different, but I think it's important that you kind of learn how to orient yourself based on these different ways of showing this. So what basically R has recognized that your independent variable of interest is society, that you have entered. So it basically gives you the degrees of freedom. So it's for society, it's 3 degrees of freedom. Residuals means that's your actual deviations. That's your deviations from your grand mean. And that essentially is here consistent with your within groups variability. So that's with a degree of freedom of 9. This is consistent with our estimate. So we have sum of squares based on that, which also corresponds with what we calculated. We get our variances, we get our F value, and we get our P value. And that's an actual P value. So what R did is what we didn't. We could have, but we didn't. So R basically calculated this mathematical function and determined where is my actual P value, where's that actual F, and how much area under the curve do I have in that function to the right of that value. So it determined the P value for you. Good. So that was the ANOVA for the societies. So now the ANOVA within groups, and that's a little trick here because for that we actually installed the R statics package. So here the formula is a little bit more complex. It's ANOVA test. That's the function. You assign rating as the dependent variable dv. You assign beer type to within because that's your independent variable. And you're assigning participant, and that's the variables that we have in our DF2. So these are our variables that we have in our DF2. So you basically you're assigning these respective variables to the actual entry. Data equals DF2, and then you are running get ANOVA table. So this runs a little longer because it's more computation. But if you do get ANOVA table, you're basically getting, again, the independent variable beer type depicted as the degrees of freedom. You get your degrees of freedom total. Within. No. 44 and 45. So you basically get the resultant F score, the resultant p-value, and here an overall p-value. So there are two differences between overall p-values and so here's where the ANOVA basically it determines a model at this point. It builds an that's a little tricky to explain. It's basically a p-value that reflects the predictive accuracy or predictive reliability of that ANOVA model. And I'm not going to go too deep into it, but it's basically an underlying principle that is basically then finding its way into regression analysis. And that's also, so regression and ANOVA, they're kind of going in the same direction. Therefore, some of the dynamics are the same. For example, the effect says the R squared, the eta squared for the ANOVA is consistent with the R squared that is a reflection of the explained variability in your data based by the regression model. So therefore, don't pay too much attention to that p-value. Focus on that p-value, because that's the actual p-value for the independent variable. So, but you ran basically the same two ANOVAs now that we did in our example. And we confirmed our findings from the beer drinker example. So as you can see, that's a very useful tool to have, because you're doing the same exercise that we did over 30 minutes of rearranging data in Excel and calculating at Excel. You did it basically in 20 seconds, if you arrange your data correctly. So that's the beauty of it. So values are the same, F score is the same, p-value we didn't do, but we see that we reject the null hypothesis that none of these are different and they're all the same. So that's the ANOVA. So now we know we have a significant difference for both examples. So we have a significant difference for our dictator game and a significant difference for our beer drinker example. Now we can basically do a post-hoc test. So two conditions will prompt you to do a post-hoc test. One is that the ANOVA turned out to be significant, that you know the two groups are different from each other, at least two. And the second one is that you have pre-planned a priori comparisons that you want to do for whatever reason your research question is asking for it. And that's why you do them. And you can do this here with line 49, Taki HSD will basically give you here a post-hoc test for all your groups. So that's basically doing the comparisons for you. So it compares foraging versus farming, industrial versus farming, natural resources versus farming. It gives you the actual difference, the numerical difference. It gives you the lower bound of 95% confidence interval. It gives you an upper bound of a 95% confidence interval. And it gives you a p-value with which you can see right away whether it's significant or not. The threshold here is, so we have looked at different thresholds with the Taki. This is an adjusted p-value that is adjusting for the Taki approach. So, in Taki, we're calculating the Q and then we're reading it from a Q table. R is doing that for you, is giving you a p-value that it can right away punch into your manuscript. So basically, we know these three comparisons are significant So natural resources differs from farming, industrial differs from foraging, and natural resources differs from foraging. Okay. Line 50. Same exercise, but we're doing it now the Bonferroni way. And we have, remember, Bonferroni, as opposed to the Taki, who's using different thresholds from a Q table. You calculated Q, which is basically calculating a standard error of the mean, and you're using the standard error of the mean to divide your individual differences. You're basically using here Bonferroni, which is basically, it's basically a t-test with a pooled standard deviation. So it's unequal variance, it's heteroscedastic, just like we did in Excel and we did in our example of the wine drinkers. So we're comparing now the different scores. So same concept applies, it's pairwise testing. So you need to follow a column and you meet the row, and that's your p-value. So farming versus foraging doesn't show a difference. Industrial versus farming shows a difference, does not show a difference. P-value of 18.5%, not significant. Farming versus natural resources, P-value of 0.04, significantly different. Foraging versus natural resources, 0.012, significantly different. Foraging versus industrial, 0.05. And that's interesting because it's slightly different than the Taki. So in Taki, we had 3 different significances. And this is why it's always good to do post-testing to make sure that you're really doing a very strict job. Why is it different? Because one is just stricter over the other and penalizes more for the small sample size. So that was Taki. Taki versus Bonferroni. So I have never used the Taki in the real world. I would intuitively gravitate towards the Bonferroni. So line 52 is doing the same example with our beer drinkers. We're comparing cheap versus high end, gives us a p-value of 0.057. So we know it's not significant. High end versus mid-range is significant. The p-value of 1.5%. Cheap versus mid-range, no different. It was 34.6 versus 34.4. So that's just not different. Okay, that was a pairwise t-test using Bonferroni adjusted p-values. That's how simple it can be. The only thing that you need to pay attention to, if you do the pairwise t-test command in a paired setting, you need to add the sub-option paired equals true. You need to let R know this is paired data. Otherwise, it will adjust it differently. The P adjustment method is Bonferroni, gives you Bonferroni adjusted p-values. Good. As for the practice lab, press Control and L. Click on the script, press Command and A, or Control and A for the Windows user. Press Control and Return. Run the entire thing down. We clear the console, Control L. We're clicking on the script, pressing Control or Command and A. Then we're pressing Control and Return, and we're running the entire thing. Then we're clicking in the console right after the eye of Bonferroni, and we slowly, carefully select everything upwards. Then we press Command and C, and copy it. We go on the spotlight, or we press right-click on a folder for Windows users. We open a new text document. On a Mac, you do text edit. We open a new document, text document. We're copying this in with Command and V or Control and V. And we're saving this all. STAT1021F, practice lab 4, and your family name. Once this is saved, just close it and submit it. Thank you very much.
Any question?
Yep.
It's still like, I tried like doing it again, starting over.